Look at this session. I'm Kurt Rutherford from Southwest Research Institute. My co-chair is Rick Elphick, and Tony here will be talking about LADEE Ultraviolet-Visible Spectrograph measurements.
Thank you, Kurt. And thanks to everybody for being here. It's fun to talk about data always. And we've got a bunch of fresh data from LADEE, which I think Rick mentioned yesterday should be hitting PDS here in a month. And don't worry, Rick, it's on track. I'm getting my news. Let's see here. So the LADEE Ultraviolet-Visible Spectrograph is a fiber-fed CCD spectrograph. I'll be real quick in the instrument description. Spend most of my time talking about science. And the mic's on this lapel, so I'll talk in this direction. It covers basically from the ultraviolet into the near-infrared, 230 to about 810 nanometers, with fairly reasonable resolution. It's just enough resolution to do reasonable point spectroscopy or line spectroscopy, but also we wanted a broad range to be able to look for dust. It utilizes two optics, a telescope, 3-inch Cassegrain grain for staring at the limb, the surface, when we do surface cows, whatever. It's our primary kind of observing instrument telescope here. And then it also has a solar diffuser optic here that we can point to the sun and watch the sun in occultation to look for very low altitude dust. And we did a variety of observations. We drove the operators mad by coming up with all different kinds of ways to point this in all different directions. It was a lot of fun. We did gather a lot of data, over 1 million spectra. Not that numbers matter, but they do when you want to get at really low signal levels. So we tried to take as many spectra as we could, as often as we could, as cold a temperature as we could manage, so we can coadd to get better and better SNR for very faint signatures. What I'm going to talk about today primarily are sodium, potassium. Those were our two primary species of interest going in, and then we were going to look for other species that could possibly exist there. We knew sodium and potassium were at the moon, but we were in a particular position where we could observe it in a completely different and a unique way than you can from the Earth. We used basically two different techniques, and these are pretty common. Anyone who knows anything about doing spectroscopy around a planet is you're always finding scattered light, especially when you're looking at signatures that are measured in tens to hundreds to maybe 1,000 and several kilorayleigh, i.e. faint signatures. Sometimes we had the spacecraft completely in shadow, total darkness, no scatter anywhere, dark surface, dark sky, that's great. And we could just measure flat out line strength. There's sodium and potassium, double it over there. Unfortunately, when we were in that position, that's when a lot of these exospheric species are at their minimum. You really are just limited by the impact vapor production, etc. During the noontime periods, when we were near noon, we would get more scattered lunar surface flux from the surface into our instrument, off the spacecraft, off struts, all kinds of different sources. But it was never so bad that we couldn't take care of it, and that was really critical. We could always subtract it off. We did measurements to constrain it. And in those instances, basically what you do is you subtract off the scatter. You can see the sodium Fraunhofer line is filled in. You can see the difference between what it would be if there was sodium and not be with sodium, and you can get at the sodium potassium that way. And both worked out really well. One last point here, I don't think I have a slide on it, I mentioned it at LPSC, is even at noontime, down in ultraviolet wavelengths below about 400 nanometers, we had very little flux, scatter flux. And so in the ultraviolet, where you have a lot of metallic species, we actually could do really nice background, no need for subtracting off scatter measurements for a variety of species. So sodium observations, there's a complicated plot for you. And I just wanted to put this one up here. You should have seen the potassium one I had before my team said, no, don't show that. Rick knows what I'm talking about. What I wanted to show was, unlike a lot of observations out there, UVS was able to measure sodium potassium at a lot of times a day over a lot of latitudes and longitudes, making these osmotic measurements. And that's really going to go a long way for helping us understand the processes and pull apart the various processes. This just shows, the approximate surface density as a function of date for a variety of solar longitudes. So each color is I've been into a variety of solar longitudes, and you can see just for this particular plot, we go from late afternoon to, in my nomenclature, 180 degrees solar longitude is noon. And in general, if we go to the next plot here, I've pulled a few of these off. Jasper showed a similar plot yesterday where you can see the sodium kind of coming up and down, and actually and overplotted here, this black line is the solar proton flux. And you can see during periods when we go into the magnetotail and the magnetopause here, and here, you'll have a strong drop-off in sodium concentrations during those periods. And that really suggests the contribution of sputtering from protons and alpha particles to the sodium exosphere. There is a lot more going on here, of course, and we can get at the photodesorption production rate, impact production rates, et cetera. And that's really where we're at right now is we've got a good data set that we put together, and now we can really start churning on the science of it. One of the more interesting facets of the sodium that we've seen, and you've seen this mentioned a few times in a few different ways, is that there's this, in addition to this kind of lunation cycle up and down here, this again shows now the number column density as a function of date. You've got the short period cycle. Then there was this broader cycle here that we noticed and we thought was very interesting and compared to Kaguya or selenite observations, which are shown down here. And I apologize to the authors for stretching their graphic out like this, but I try to line them up. And this was always kind of a mystery too that selenite saw. They were looking, this is data from the sodium tail that they were observing, and it had this kind of also similar trend to it. And we've got a more complete data set over a maybe shorter period. We go a little bit further in November time frame than they do. But there's this interesting long-term cycle of sodium that I think is quite interesting. And so far, the only thing I have been able to correlate it with, and this needs a lot more study and looking at, is possibly long-term variation or annual variation in the meteoritic flux. And so this shows a slide that Tim Stubbs let me borrow here, and it shows the integrated impact vapor production rate as a function of time. And I just took the previous, if I go back one here, and I made up this curve. This is not a fit. This is a PowerPoint fit, so don't hold me to it. But I did it there to help just with the eye. There's some kind of cyclic variability there, and we're looking around. We're thinking, well, what could be causing that? What in our orbital variation could it be, or anything like that? And one possibility we've looked at is that there is an increase in production from impact vapor that is around the late winter or late fall, early winter time period that does drop to a minimum in late winter, early spring, and then comes back up again. And this curve is the same curve I just showed above, where I've kind of put together LADEE and Kaguya observations for the sodium. And boy, wouldn't it have been great if we went another 6 months to get the rest and really get at this. But what are you going to do? It's something that we really are interested in and going to study in more detail using both the LDEX data as well as more studies that Tim is doing on the impact flux. Because I think one message I'll say right now that's coming out of the data for me is how important impact processes are to the exosphere, probably more so than we ever really appreciated. Moving on to potassium, this shows, and Rick showed this yesterday, a comparison of some sodium-potassium measurements that we're looking at. This again is noon, I call noon column density, so it's around the noon local time that we derive this data as a function of date. And it's for both a noon, okay, I have noon here, and then there's sunset over here. So it's noon and sunset data. So sunsets, later in the afternoon, quite late actually, and then noon, and they're on two different scales because they're obviously at different concentrations. And I just overplot them like this. Here's the sodium that you just saw, and here's the potassium. And while there's some obvious resemblance to each other, there's this cycle with the lunation. There are some differences, and in particular, I'll point out one because there's so many we could spend a lot of time on it of interesting things. That the sodium clearly starts to drop coming into the year. And it almost looks like the potassium wants to, and then it starts to climb back up again. And that's pretty interesting, and we think we might have a handle on why that could be. And there's a couple, and I'll get to it in this chart, but this shows two important points as well. This shows, again, the approximate surface density for potassium as a function of date, and I've overplotted it with the proton flux. And I've written up here, it shows some correlation to the proton flux, but not as cleanly and obvious as perhaps the sodium does. But if you stare at this long enough, you can see where both, where you have these kind of peaks of proton flux, you will have peaks in the potassium as well. And actually, when you run a correlation algorithm across this, it's in the 50, 60, 70%, depending on the time of year, what period you're looking over. So there is some correlation to the proton flux, but it's not as obvious as the sodium. And it's related to the same reason, I think, at least right now, as why we see this starting to climb up rather than dropping off as the sodium did. And that's because of potassium being much more tied to the surface composition. This shows the latitude and the noon column density here for potassium. You can see as LADEE moved in time, as the LADEE mission progressed, we slowly were moving upward in latitude, higher latitude, starting at around minus 22 or 23 degrees, and by the end of the mission we were around minus 12 or so. And there's this clear increase that you don't necessarily see in sodium or any of the other species we're looking at. Potassium has this clear increase with altitude, and that makes sense. If you saw Mehdi's talk from NMS, you've got this high concentration of potassium in the creep region. As we're moving over higher and higher concentrations, changes of a couple orders of magnitude in potassium, we could actually be seeing that in the potassium exosphere, where we're looking as well. One possible idea needs to be really fleshed out. Another nice thing about the potassium profiles, though, is our data set is we get some very clean profiles right now, looking at them as a function of altitude. And we do this because the spacecraft is changing altitude, and we scan with our telescope at a variety of altitudes, so we can kind of look at a range of altitudes there. And this shows the column concentration of potassium as a function of altitude, and each of these are various solar longitude periods. So you can see we go from one terminator all the way to the other terminator, and where we have there's a lot of potassium, we have a lot of signal, and just a nature of the orbit and the way we viewed as we pass noon and we move towards the morning terminator. Remember, in the retrograde orbit, we get more and more scattered light. Thanks, Kurt. We get more and more scattered light, so our air goes up. So that's that pesky scattered light getting in, ultimately. But we can still use these to really get a much better handle on the low near-surface potassium exosphere. And I've kind of summarized it here by doing a couple fits. This is very initial stuff. We're going to do more sophisticated fits to Chamberlain profiles, etc. But just using a couple hot and cold exponential fits for the scale heights, we can derive the total surface density as a function of solar longitude for a hot and a cold case, where N1 and N2 are the two cases, N1 being the cold population, N2 being the hot population. And I plotted that here, and you can see we generally do get a trend that is cosine in nature. I've plotted a cosine squared. These plots, again, are these points here. We have a lot of that scatter, so I don't necessarily have a lot of faith in them, even with these error bars. These are 2 sigma error bars. But what you can see is it is certainly shifted to later times in the afternoon, and that's what many theories have predicted. And we can look at the scale heights as well, as they vary with solar longitude. In general, the thermal component minimum is near noon, slightly rises at later times, and a lot of this is somewhat what you would expect with changing temperatures at the surface. But what you did see is it really changes, the concentration just changed with date, i.e. changing with lunar phase. And so we are looking at how this changes with lunar phase as well, and there are indeed changes in the scale height with lunar phase. So it's a very complicated data set and it needs to be pulled apart, but we've got the data now that we can really compare to models of what the potassium exosphere should be doing, comparing it to sources and sinks. So real quick slide on summary. This is basically the same thing I had at LPSC, so I didn't want to change much in here. We're really excited about the sodium-potassium observations. We've got this great data set. At the time of LPSC, we weren't pulling out the 2 terminator concentrations. We are now with a lot of confidence. And actually, in this year, part of our plan is eventually make all that data available on the PDS, including the raw data. We're going to publish all of our derived sodium, potassium, and other species so that it'll be easier for the community to use in general. We are looking at a variety of other gases, and out of several other slides in here we decided not to show for sake of time. But it is a much more rich spectrum than I ever thought. It's not just sodium and potassium. We see many lines. We can co-add literally 30,000 seconds of integration time with no scatter. And there are lines there. And this shows, the blue shows where we have tentative detection, and by detection is we're confident and we're actually mapping them in the same way as mapping the sodium and potassium. We can map them as a function of time. So we want to get that through a review process, though, before we say a whole lot more about it. And lastly, the one point that I didn't talk about here is dust. Dust is, we are certainly setting new limits. There's a poster Diane Wooden has on dust that her and Amanda Cook and others have been working on. So I invite you to that poster and we can discuss our dust results there. Thank you. Thank you.
One quick question.
Could you just go back once so I can absorb everything?
I'm trying to do the same thing. That's why I let me go over.
But you can have the slides.
It's all online already.
It's all online.
So go look at it there. Yeah, play it over and over again. Let's get Dean up here and thank Tony one more time. Thanks.
Thank you, Kurt.